Okay. So sorry for the delay. So let's start. So today we'll just do a review of concentration and maybe see some connection with geometry. And then the next few lectures will be about concentration. So let's start. Yeah. So what is so before we start with concentration, let's start with some very basic arguments which underlie many of these things. And which many of you might have seen. So let's start with what is called the Markov argument or the Markov inequality. Okay. So it says something about it addresses the following situation. So x is a non-negative random variable with mean with expectation equal to with expectation ex, right? Whatever mu. So the question is, what is the probability? What can you say about the probability that x is bigger than t? Let's say. So the inequality, of course, everyone knows, and so I just want to quickly just recap it, and it's a nice argument. It's the argument is good to keep in mind. It's an averaging argument. It's a very simple argument, but it's very useful, not just in this context. Also, like if you have both-sided bounds, both-sided inequalities. But let's just see what it does here. So well, you just say the following. So well, we know that the expectation is mu. So the expectation can be broken into two parts. Expectation can be broken into two parts. So this is the triviality for this one. And then you say, well, okay, and this is what is called the Markov argument. You say, okay, both of these things you bound in slightly different way. Okay? So this side, so this side you say that okay, this side is bigger than. So here x is certainly bigger than t. So let me put greater than also. Plus, what can I say about this one? So this is particular case, it's at least 0. So plus 0 because x is. But maybe in other contexts, maybe you know more about this and you can say more. So then you can get this one. So that is why the argument is very important. And now it's the inequality is easy. So this is just t times the expectation of the indicator variable that x is variable, that is the probability. So this is right. So this gives you the standard upward taper. And you can now try to think about when and what we made strict. So that's a good side too. Yeah, usually this is good, no? It's good to think about what can be made strict. Okay, so that's the simplest one. Let me just make sure. Yeah, okay. So that's the simplest one, and now let's look at one thing you can do with this is so this seems a bit weak, but it's actually quite powerful because you can apply it to any random variable with non-negative. So if you have some random variable, you can apply from function, you can then apply. Again, I'm sure all of you have seen. So let's look at the missing. So for example, the higher moments. So higher moments. Right. So for example, what we could do is so let x be any random variable. With variance. Expectation of which is right. So x minus is equal to sigma square. So this is the definition. Mu expectation. Okay. So then clearly, then y equals x minus mu squared is a non-negative random variable. So you immediately get that. So the probability that x minus mu is bigger than t, which is the same thing as the probability that x minus mu squared is bigger than t squared, right? Because these two are the same events, and that is less than, by Markov's inequality, expectation of x minus mu squared by t squared sigma squared. Okay. So this is just a recap. So this also, so you can apply to that. Another thing which works like that is called a Laplace transform method. So that is trying to use all the moments at once. So it's useful analytically. We'll come to that. So this says, well, like for any random variable x, any real t, expectation of x tx. So this is often, yeah. So this is called the so this you think of as a function of t, right? But it also, of course, depends upon the distribution of x. Right? So this moment generating function of x. So why is what called the moment? If you expand it out, so it's actually in the terminology of generating function, the exponential generating function of the moments. Right? So if you expand it out, the coefficient of t to the power k is exactly the kth moment of x divided by k factor. So that's called exponential generating function. So the usual generating function would be that the k factor is not there. But yeah, so this is the moment is the exponential generating function of the moment. Okay, so yeah, so this is not, of course, non-negative. So, for example, if e.g., if t is say positive, then the probability that x is greater than equal to some s, right, is which is the same thing as the probability that x of tx is greater than x of ts, because e to the t times x is a strictly increasing function, right? And this is less than x minus ts. So the power of this comes from the fact that now this is true for every positive t. So in principle, one can start optimizing. So it just helps to maybe slightly different. So this is equal to x of which is, so this is called a log moment generating function for every. Okay, so you have that psi x is defined to be log of e of x power tx. Okay, so this might not always be defined, by the way. So for some t, this might just not be defined. So it might be defined. So it's maybe again an example where that happens. But yeah. Okay. So I mean, also the movement generating function also may not be defined, and therefore this may be defined. For certain values of t. It might also be the case that it's defined for small enough t, but not for all t. So that. So yeah. So then what you get is so you get something like this: that the probability of that x is bigger than s is less than e to the power minus supremum over t non-negative of ts minus psi x t. So if you, those of you have seen some like what do you call it? The Lajan ritual, might see that this looks a bit similar. It's not exactly the same because we have constrained that t non-negative, but it looks very much like. So in particular, it's a supremum of the linear function. So it's convex as a function. Whatever is happening is convex as a function. So often the game is to get good bounds of this and then find this figure. The calculation looks very much like in the song. Yeah. So that of course this competition depends on what the distribution of x. So one reason why the Laplace transform thing is very powerful is because if you have independent random variables, then it just nicely translates. So one reason for why it's useful. So it nicely tensorizes. This you can see very easily. But even if things are slightly like, for example, if you're marking, there's still you can. Okay, so this, as I said, is mostly a review. So, but any questions so far? Okay, so let's again maybe one more thing as well. So let's at least do this calculation for one the like, this is okay. So competition of this class. So it also like says what is going on. But before that, or maybe yeah, we'll just. So okay, so example would be example. So let's look at Hopding lemma, which gives which bounds the Laplace transform of a bounded. So the setup is so the lemma is let x have let x be so x is a random variable. with mean 0. So then so let me just put a C here. You'll get the correct C, but it's for some there's a constant C and it's quadratic form. Yeah. So the mean zero thing is not really a constraint. You can always subtract them. Otherwise, you just get whatever that. It's not really, it doesn't affect anything. Just to simplify the statement. Okay. So how does it prove this? So there's not much we have, right? So we just have the sorry. So this psi x of t is log of e of x of tx. Okay, so especially if you have seen some physics thing, then you might notice that so then this might look very natural. So this is like a log of a partition, and or I mean not necessarily physics, even in commentaries, when you take these kind of logs of some generating function of this kind and take derivative, those things give you means, right? Because this whatever this is here will get go to the denominator, and then you will get the corresponding. So this is a very this looks very sort of vague, but it actually works always. That's what we compute it. The derivatives are nice interpretation because they will correspond. So computing derivatives is very natural, but the point is that the derivatives are nice to deal with because they have this interpretation in terms of, and that interpretation will help make it easy to think about what is going on. Right? So let me just for simplicity, just call it f of t, just to keep x also. So what is f of 0? Just 0. What is f prime of t? So yeah, so this is the thing I was talking about. So let's just see. So f prime of t. So I'll just do all the differentiation things. So engineering method, like assume all derivatives, all of them exist. In this case, it's easy to justify because everything is bounded. There's nothing really wrong happening, but I'll not worry about this. So now, so there's log and all this there. So this thing goes in the bottom, right? And then you have the derivative of that. So the derivative of that looks like, so again, the derivative goes inside the integral, and this thing becomes x times x. Right. So I was talking about things like means and so on. So does this look like a mean? Yeah. Okay. So one. Yeah. That is. Yes. So there are two things. One is that equal to 0 clearly it's a mean because this thing is 1, that is 1. Just the expectation of x. So f prime of 0 is equal to expectation of x, which is equal to 0. Okay. So this is nice. But also at other points it's a mean because it's just another distribution. This is a distribution of density with respect to the distribution of x is e to the dx. And that's a probability distribution because it integrates to 1. Right? So think of, but also suppose, so let whatever, let mu denote, mu I was talking about, calling mean, right? So let alpha denote the distribution of x, and let beta t be the probability distribution whose density with respect to alpha is x of tx divided by expectation of x of capital. So at any point x, it's So this is the correct expectation of this density is one. That's what correct quite definitely. With that distribution, so f prime t is the expectation of y distributed according to beta t. So it's a mean. So what about the second? Yeah, so this is actually so it's another name for these. We just call like so the log is for and this is a common phenomenon. Any kind of partial function thing will always be first derivative mean, second derivative some kind of variant. But when you take the log of the partial. So and that has to do with like yeah, so this form this gives like form like e power one. And that's what we're differentiating them. So now let's look at f prime of t, f double prime of t. So f double prime of t. So yeah, so you have to differentiate this f prime of t once more. So this becomes expectation of squared. So let me write it slightly differently. So it says e of x squared x dx divided by x power x dx minus e of x dx and this is just the expectation of y to beta t of y squared minus expectation of y t y squared, which is just the variance as y. So note that y it may not mean zero, but it is in the same range. Right? Because the density of x is zero outside, that's the density of y also zero. Beta t has zero density. Okay. So now what? Now what can we say about f prime t? F double prime t. Yes, the variance is now bounded, right? So the variance cannot be so. So in many ways, think about it as I mean, the variance of some random variable range should not be more than the square of it. Right? So it certainly is less than a minus b square. Why is that? Like intuitive bit state, but analytically, the mean is on one hand. Yeah, the mean and mean also is the same interval, and so x minus ex, each of those terms is mean. The whole thing that must be minus a squared, but actually slightly better than that. One quarter. So yeah. So why is that? So certainly, certainly. And this is good enough for us. Well, modulo one Taylor series argument, it's good enough for us. It gives us t squared x. But just to make it tight. So the point is that so the variance also has this property that if you look, so this extremal things are always good to keep in mind. The variance is what? It's like expectation of x minus expectation of x minus expectation of x whole squared expectation. Right? But you can think of expectation of x minus a squared, the squared deviation from any point. The variance minimizes and it's easy to see why. It's like it's basically a version of whatever. Huh? Yeah, it's basically a version of Pythagoras type stuff. So let's see. So the point is that, so note that expectation of, so let me just write it as anything. Expectation of z minus a squared is equal to expectation of z minus ez plus ez minus a whole squared, which is equal to variance of z plus 0 plus a minus ez whole squared, right? For every a. So the variance minimizes when the expectation minimizes, and that minimum is the variance. Right? So therefore, this variance of y in BT, so y is less than, I can put any a, and the one good a to put is the mean point. So it's the expectation of y minus b plus a by 2. But now from the midpoint, any point is the distance at most c b minus a by 2. Right? So this thing is less than. Okay. Yeah, and now we are done. So now we just use Taylor's theorem, and we just use the fact that now by Taylor's theorem or by mean value theorem, or really anything. Yeah, so there are many ways to now justify it. Like, let me just say the mean value theorem. So f of t is less than or is equal to f0 plus f prime 0 times t. And yeah, so this is the thing. So plus f double prime of s by 2 times t squared for some s in 0t. Right? And we have shown that these numbers are all this is 0, 0. So which is less than b minus a squared by 8. So yeah, so this looks like I'm not even calculating, but again, yeah, this is again revision. This turns out that like the nice sense is actually equivalent to Pinsker lemma. So you can see that in classes. And that also is useful. That way of thinking is also useful for concentration inequalities. So yeah, T square. Sorry, at the end. Yeah, T square, T square. That is important. It is very nice. Yeah. So yeah, so the C is 1 over it. This immediately, yeah. Oh, okay. So what do you do with this? So, so this, for example, immediately gives you the Chernow inequality. So why is that? So yes, again, this is we have seen before, but let's just do it once. So from this, for example, the probability that summation xi is greater than 1 over n summation xi is greater than 1 over n summation mu I plus s, where xi are in AB, AIBI even, independent, and mu I is expectation of xi. Can be bounded as Right. So remember, so it was this thing, right? So TS minus sum of the things. So the sum is yeah. So one thing, better nicer thing is to just multiply everything by n, that like becomes ns. So I will put nts. So multiply here by n. Then apply like so, like we have to keep track of more factors. But yeah. So minus summation 1/8 pi minus ai whole squared. Pi minus ai whole squared. And this is an easy calculus exercise. It's a quadratic of this kind, right? So, and you want to maximize it, so you just set the derivative to the next one. So yeah, so the minimizer or maximizer is at t equal to ns 4ns by summation ps. I think that's correct, right? Yeah, something. And now you put that back in, and so you get so. Let me just make sure that I'm getting this correct. Some constants might be off, but let's just check. So yeah, that's correct. Yeah. So this no, something is not right. It's everything. Okay, good. So yeah, so the scaling with n is not only n squared, it's n, because the thing below is also a order and also the order n. So scaling with the uh, number of sums is n, into minus n. It's the scaling in the perturbation or whatever the error s is squared. So this is kind of important. This is often the one reason why things like 1/s squared log 1/. This comes up from here. Suppose all the BM and A are all equal. This is like 2n s squared. Let's say BM and A are all 1. So and random is 0 1. Then there's 2n s squared. And to get error delta, get error probability delta, how many samples do you need? So now you think about it, it's exactly so log 1/delta, 1/epsilon. So if you want to get error at most s, probability at most probably at least 1 minus delta, then the scaling is 1/square of the error. That sort of is not beat of anything else. And log of the error probability. So that this at least captures that. This thing is also called sub-Gaussian. So Gaussian also has like p minus square. So the opening inequality is saying that bounded random variables are sub-Gaussian. And the sub-Gaussian parameter is square of the interval. So for me, yeah. So sub-Gaussian basically just means that, right? But sub-Gaussian just means that something of the same. So you say that sub-Gaussian is psi xt is less than t squared or something. So here p minus h corresponds something. As soon as you have sub-Gaussian, you get that response. And for the same thing, so sums of sub-Gaussians are also sums of independent sub-Gaussians are also. The C is then called Yeah, what is called a sub-Gaussian parameter can differ from other to other, but yes, C is some kind of a sub-Gaussian parameter. So if you define that in a sub-Gaussian parameter, then it's empty. But if you define it with the square root of this, so it acts like even you want to define it. Uh, yeah, it's not very good, but yeah, I mean, any number of things are called sub-Gaussian parameters. But yeah, the crucial thing is that roughly they add depending upon how it is. Either they add or they square add when you have independent time. And yeah, and this is just one example of the sub-Gaussian. I mean, another function compute. There is the exact calculus. Okay, so this is called, I think it's called a Hoping inequality. Actually, it's more general. It does not require independence. So that maybe will be in the homework. But that was not pretty sure. Okay, so far we have seen some very classical things distributed and maybe a little bit more of it. So one question one can ask is where do all these things come from? Like, I mean, here it seems very analytical. We just did some calculations and these things popped out like this nice exponential decay and so on. So where did the exponential decay come from? Is there something more fundamental going on? So there's some one nice geometric connection. It's also useful sometimes in proving inequality. So let's just go through that. Uh, so let's just so let's see. So let's see why we might expect. So why might we expect something of this kind? So where else will something of this kind show up? Some error bound of this kind. So this will be a bit philosophical, but yeah. So where do concentration inequality? Yeah, this is maybe too ambitious. Yeah, and not everything might be fully correct also. But yeah, let's just look at this. Suppose X is a Gaussian. Suppose X is n01. Then it has something of this kind, right? So let's say if I look at the probability that X is bigger than T, right? Is equal to some 1 over root 2 pi T to infinity X minus X. So this is a calculation that again will be in the homework, or you might have seen it also. So this something of the kind. So okay, so it has this thing. So at least, so this is like it's like saying that that inequality looks a little bit like how this. I think very. Uh, so it's like I'm drawing these lines here, like there's a line at T, and I'm saying what is the mass of the Gaussian thing, which is going beyond that. And it's bounding that, it's saying that that is small. Somehow that kind of number, that kind of thing is what is showing up. Okay. So so it turns out it's okay. So that's good. So and now we can even start thinking of like higher dimension going for like more and like independent, large independent process. And again, if we say something like, what is the probability that say any one of them is larger? Again, it's kind of thing. Because others are all free, and so like hyperscale. And because it's one hyperplane at a certain distance, and because of like the higher dimension Gaussian, so if I just take independent copies, they're spherically symmetric. So all hyperplanes are the same. So, so, so this somehow seems to be something fundamental, even though it's a one dimension. So what I'm saying is, if I take the n-dimensional version of this, so the n-dimensional Gaussian, which one can think of as just n independent copies of that is very symmetric. And my thing is, what is the probability that if I take anyone like this is at a certain put a hyperplane and say what is the probability that the mark goes outside this? Then really it's just a one-dimensional calculus. So I can just rotate that hyperplane down to one. That's not roadmap, but they're coming. And then it's just the same thing. End of the picture. So okay, so this so but the thing is that like this somehow this hyperplane is showing up here, right? And we are looking at how much like sort of yeah. So like see if I so and we are looking at how much is outside. So this so yeah so this so it's roughly like this. So it's like there is a set left of the probability of, and then we go a distance away from it to distance t, and you know that whatever after that whatever that comes is extremely small. So in some sense, there is a nice thing that we can think, move a little bit, then have covered most of the thing. So the thing is very small. But the question one can ask is it true for one such set of volume harm? I took one such set, it was very specific set, right? Which is even the case it was like hyperplane, like the hyperplane which carries half the volume. And then I said, okay, here's hyperplane carries half the volume. I go distance t from it. That is just translating that hyperplane parallelly by distance t. And then again I get the same answer. For these things, the answer seems to be very nice. Like you go this distance and you cover everything, right? Or more or less everything. Like you're covering half the thing, but then you go distance, you're covering everything except e to the power minus t squared. So that's it's became very it's like or you're covering things very fast, right? So what does this sound like? So if I this set, it's like it has a certain surface area that sort of seems to be large. Instead that I have this volume, and if I make it a little bit thicker, I cover almost everything of the area. So making the surface making it a little bit thicker is sort of like saying the surface area is large. So at least for these sets, the surface area is large. The question is, are there things which have much smaller surface area with the same volume? So why is that important? Sorry, yeah, okay, so let me actually write it. So we can also so maybe let me write what I was just saying. So so now if x is in n0 I and still and and we take any hyperplane given by uz equal to t, where u is a unit vector, then the probability that x u and t is exactly equal to the probability that n 01 greater than t, which is less than. Okay, so this was that, and then you're saying that. So let's think of it like this. So we're saying that the set like that for any hyperplane uz equal to 0 to the origin. For any half space, let me say any half space uz say less than equal to 0. So this is the left side like this. This is the origin. The set of points at distance at least t has small volume. Right? Now the half space itself has volume 1/2. The things outside t have volume really small. So this thing in the middle must have large volume. Whatever is remaining there, half minus like so. The total volume of this whole thing is 1 minus something very small. This thing is half, so it should be half minus something very small. So this is just saying something very obvious. So this whatever has been thickened, this small. So
you're calculating surface area by saying that okay, I paint the thing with a
so that is so
much paint.
So the definition of surface area. So the question actually is yes, I didn't want to, but yeah, this it's actually not surface area, but one natural thing mostly is that you have a surface, you thicken it, which means that every point in the set. So forget about surface. Think of whatever is enclosed in the surface. Now you want to compute the area of the surface. For every point in the set, you put a ball of radius epsilon. Some of these balls will be inside the enclosed area. Some of them will be outside. You just take the volume that is outside, which is not in the open set, and subtract. So that's or in other words, you take the all the balls, take the volume, and subtract the volume. That's whatever is left. That's a thickening. And that you divide by epsilon and take the limit of epsilon goes to 0. So if you try this, so usually for all, I mean, not for all the natural things, it will give sometimes it will not be defined and so on. So you have to work harder to define it. But at least it's a natural definition. So in that sense, so in many of these applications, it's easy to think of the surface area. Like I have a volume, I figure a little bit how much does it increase? How much the volume is as a fraction. So if I figure it by delta, this new volume that I get, what is it as a fraction of the original volume? Here I am filling in, it's actually quite large. It's almost 1. So because so it's like this new volume is half minus delta. Half minus something very small. Half minus that error. And the original volume was half. It's like almost 1 minus that. So that should be the volume by the thickening parameter. Yes, that's what I said. So the surface area, you take the original thing, you add a ball of radius epsilon everywhere. Then you look at this, the whole volume of this union of these balls. Subtract from this the volume of the that's whatever is left of the volume. Yeah, and that divided by epsilon is the limit. It's already complicated. Take the limit. I mean, which might not exist. But yeah, it's very. But you often it works. But for sphere, you can do this calculation. Cube, you can do that. So for corporate context of a standard surface area is again you can find the same way. Yeah. Just the density of in that way. So yeah, so it's not clear, right? So like the Gaussian density is not even defined. Like I'm talking about the theory of us type. So let's not even. That's why I wanted did not want to say surface. So then all these random measurability equations come. So it's much easier to think of just how much is the volume changing when I do a small thing. That we just think of as some rough notion of surface area, and it's usually more useful for like doing. So the other one is more elegant sometimes, but for calculation because you're thinking other one is n minus 1 dimensional notion. You have to go from n to n minus 1 dimension and come back. This all usually always troublesome. So yeah, so this notion is n dimensional. I have a volume. I'm thickening it a little bit. and see how much is the area, the volume. How much is the volume? So, um, so this says, so or more sort of numerically, this, so volume of the, so yeah, so let me take the half space plus this ball of radius t. That is what minus the volume of the half space divided by the volume of half space is pretty, yeah, it's like 1 minus 1 by is greater than or equal to.
You have a multi-dimensional integral. You're not extending it to a half plane.
Yeah, so that thing will give a density. I mean, here of course you have a density. Yeah, so it will agree with that. But yeah, but in many cases you want, like, I want to talk about these things. For example, if you have a body, just a particular body and take any arbitrary set in it. So again, the density is there, but it's often like, okay, right now it's fine. But the next thing I'm going to talk about, then this thing might not look so nice. So the thing is, so what I want to say is that, okay, so for one thing we computed, whatever is process of density, right, is something large. The question is, are there other things which have much smaller surface area of the same volume? So are there sets of volume half in the Gaussian method which have much smaller surface? The answer is actually no. It's non-trivial result, and instead of actually the lowest surface area is usually the isoperimetric inequality for the curve. And this immediately, if you think about it, gives you concentration for all electric functions. Why? Because you take the median, right? So you take, for any electric function of the Gaussian, take the median value of the function. And you look at a set where the function is less than the median value. That's exactly something which is volume half, right? Or at least a half. Right? And now it's saying that if you thicken it a little bit, it covers at least as much volume as this, because this is the one with the lowest surface area. Which means that the probability that it goes T more than the median is so this is a nice connection between isoperimetry and constant. That basically what, so the thing here is, often you don't prove things like it, but what is the thing that there is some nice set where you can calculate the surface area exactly, and then that set often turns, I mean, whatever turns out to be the worst case. Other function. So now I'm saying that I take the Gaussian. So here you ask, I'm taking x, I'm taking any elliptic function, one elliptic function of x, f of x, and I'm saying it concentrates around it with the same thing, exactly the same. Okay, so let's yeah. So let me just write that. So this surface area. So this you think of it as a surface area of half space is somewhat large. Volume half. Volume 1/2. And I mean, and all the volume 1/2 spaces that you know what they are, right? For the Gaussian. I mean, they all have to pass the order. And I mean, and they are all the same. One space is large. Okay. And then and Gaussian isoperimetry, this is a non-trivial result. The Gaussian isoperimetry says that among all, yes, I'm not writing it formally, but it can be made formal. Among all the volume half sets in the Gaussian measure, This is essentially the worst. Okay. And if you have these two things, you immediately get. Okay. So yeah, worst case as in yeah. So like everything else will have even more circles. Yeah, this is the worst case. This is so the smallest. So in this sense, this is the time of surface area. And that's why I think it's more useful because now with this sense, it's immediately the ellipsis thing is immediate because the B of t is exactly that set. Right? So if you have the set f, and I want to think where is the function. So the median is m. I want to look at a set where the function has value more than m plus t. So I have to go at least distance t away. And then it's exactly so. So this is a notion of surface area. Okay. So we do proofs of Gaussian conjugation also. And sometimes actually they do go through another notion of isoperimetry, like more. These are like a more integral note, right? Like you're saying, this is the one with the worst surface area. You can also get more differential notions, which is in terms of random walk. Certain random walks have no bottlenecks, and those also imply those more analytically imply uh, conflict. Even more general, not just for conflict, but for any. And so we'll see examples of that, like how those kind of isoperimetry statements somehow imply concentration. And those kind of isoperimetry statements are often for the yeah, but this isoperimetry thing is still good to know. Yeah. The connection is there. So this immediately gives the Gaussian concentration inequality. I think this is called the Gaussian concentration inequality. And it has many people's name attached to it. Srivastava, before movement, but I can't remember. I put them. But the probability that if x is n0 and f is 1 Lipschitz in. So what does that mean? That fx minus fy absolute value. So fx, a real valued function, is less than the 2 norm. So there you go. And probability that fx is greater than m plus t is less than some. I don't want to get into a debate about whether the median should include the half or not. So yeah, and it's also just useful to just say it this way, so it satisfies. Um, uh, yeah, it satisfies that the probability that if x is less than n. So in some sense, it need not even be a median. Just something which is like at least as good as. So it'll be to put median in quotes. Okay. So this is just translating. So yeah, it's a pretty useful. I mean, it's a pretty powerful statement. For example, so what can you apply it to? For example, if you have random matrices with Gaussian entries, their eigenvalues are lifted constant. You need to show and you immediately get constant. So it's that powerful. So any question? Yeah. So like so there's one thing about Gaussian theory. As soon as you have some nice set which has good surface area and you have an isotope, you get it. So the only thing that depends on Gaussian is. But the estimate depends on the fact that it is. Sorry, what? Just this. Yeah, just this. But the rest of the argument is very easy. Yeah, or whatever the worst case scenario. So we'll look at just one more example. So you can do the same thing on a sphere. So it's maybe not surprising that you can do it on Gaussian. But surface of area is slightly different because it's like taking a slice of the Gaussian. It's not a ball. So again, so you can think of what should be the isoperimetric. But before that, are any questions about this? Actually, that Gaussian isoperimetry for the Gaussian isoperimetry, I think it's more stronger. I think it's there that for any volume, that minimizes the surface area is the half space of that. Something. Okay, so let's look at another example. So which is the uniform distribution on the surface of a sphere. So again, let's try to think of the same thing. So what are the natural the most natural one? The hemisphere, right? So you can think of like this. Okay, and let's see if I can do this calculation off the top of my head. And now, what's the natural notion of distance? So it's like distance along the street. This straight line, about geodesic distance on the street, which is like arc length. It's nothing more complicated than for any 2 points you'll find a great circuit, which is like so you want to find a plane that crosses to the origin and those 2 points. There's only one defined. So you take these points and so you have a great circle, and then it looks now you're in a plane. So yeah, so that arc length is the. So you look at whatever, like you look at some thickening like this, and then you ask for what is the volume that is left. So this is nothing very small again, like it's very high dimensions. So it's for unit sphere. So it will turn out to and between coordinate spheres is that for any given volume, what should be the statement? For Gaussian, but what is it in the Euclidean space? Or what's the isoperimetric thing about in the Euclidean space that everyone has heard of? How maybe not really true, but what is the involved for the Lebesgue method? Yeah, the wall minimizes the surface area for a given one. For Gaussian, we saw that half space is changed. What should it be here? Yeah, hemisphere for volume half, but other ones like there might be other volume set like that. No, so the hemisphere is volume half, but of course there are sets of smaller volume. Yeah. So what's the natural?
So if you take the circle, which is parallel to the
Yeah, so it was caps. Basically, you cut it with a plane. Yeah, cut it with any anything. Yeah, yeah. So basically, anything you just when you draw the thing, it goes like it's the. So it's called a cap because yeah, so when you cut it with a plane and you draw from the center the line, it's somewhere here, and then that whole thing looks like a ball. Right? I mean, it looks like all points up to a given distance from the point. From this. So the hemisphere is centered here. So it's all the points which are half circle, at most half circle. So from the quarter. Yeah, quarter of the so, and yeah, so for the general case, it would be so it's very good. So the isoperimetric case. So these are again this is a non-trivial result. Isoperimetry. So again, the surface area definition is the same as before. And the lowest surface area. Yeah. Yeah. So I'm being a little bit. Yeah. This is actually a stronger claim for any reasonable, like large, any small t, any small enough t, up to a certain big enough bound. The optimizer is still. The surface area thing was just so that in the limit t goes to 0. But we are saying that this is a stronger thing. Any small. Yeah. And small enough is not really small. I mean, it's like any. All here is all. Yeah. All. Lowest.
Not just the limiting statement, you need that small enough t.
Yeah, that is important. Yeah. That's why this notion is sort of more. First of all, it gets rid of all the major theoretic problems. Yeah. So then we just need to do this calculation for spherical cap. Then just try to do that. I'm pretty sure I'll pair it. Okay. Yeah. So then we just get it for a ball. No, 3D sphere you won't see anything. Huh? No, you have to see anything interesting, you do it align them and with that. Yeah. Otherwise, No, I'm not going to prove isometric. I'm only going to say, like, basically get the form of this. That's all. So this we will not prove. So we try to do this calculation for the half. Okay, so forward to prepare first, but let me just try. So okay, so the way you do these things, which usually works, is that so is similar to how you would do in 3 dimensions. So I'm trying to compute some surface area. So first of all, I just assume one of the axis, and so then if I look at say one slice here, right? So let us think about what that is, right? So the slice cuts this here. So this is Sn, right, or whatever. Let me just say Sn, right? So it's embedded in n plus one dimension, n-dimensional surface. So what is this slice of the surface? So when I take the slice on the surface, what do I get? It's some scaling of Sn minus one, right? So, and what is the scaling? So if I'm at distance, if I'm at angle theta, let's say, right? So the radius is, radius of the original thing is 1. So the radius of this guy is cos theta. Right? So okay. So now yeah, and this is where I'll ask you to take me a little bit on faith. But so now if I want to compute the full surface area, so if I go a little bit like this, so this d theta. So the surface area of that part is how much? So this the surface area here is, so let me give these things names. So let's say surface area of Sn is called something. Let's say, I think this is the usual terminology is to call it sigma n. So this part has sigma n minus 1 to the power cosine n minus, right? Because it's that dimensional object, theta, times d theta. Okay. So yeah, so this together, this whole thing says that sigma n is equal to 2 times sigma n minus 1 cos n minus 1 theta d theta 0 to pi by 2. And what we are looking for is up to some small theta. So what we are after. So the volume of a, let me call it phi thickening, because this is just okay. Yeah. Yeah. So let me just make sure that this actually works for something that we know. So I put n equal to 1. Then put sigma n minus 1 equal to 1. No, yeah, sigma n minus 1, so I should put the counting measure, it's 2. So it's pi and 2 pi. So that's correct. So there are 2 points. Oh. N minus 1. But it has to do that one. N equal to 2, I think it works. So n equal to 2. So if I put n equal to 2, that will be 2 pi. So this is 2 pi. So the whole thing becomes 4 pi. And then I'm integrating from 0 to pi by 2 cosine theta, which is an integral of 1. So, it actually works. Yeah. It should work. It's a joke, but it's also correct. And I mean, it's really like you're doing it once here. Yes, like what is the arc length of these two arcs? It's like 2 times 2 times this. So actually, no, this if you really feel adventurous, sometimes there is a nice for some definition lines. It's on YouTube. Okay, so there's a book called Geometric Measure Theory by Federer, H. Federer. This counting I think can actually be generalized. So there are things that you actually do count and then integrate, and it actually can be made very rigorous. It's nice. So that book is focused on many such different. Surface area of the one dimensional sphere. The volume of a pipe thickening is so yeah. So this I should now do. So the thing is sigma minus one will go away. It just becomes some integral of this kind. So is what? So it's integral from 0 to 5 of sigma n minus 1 cosine n minus 1 theta d theta divided by 2 times 0 pi by 2 sigma n minus 1.